this problem, we have, let's see here, we have a Rankine cycle with a regenerative phase to it. We have a net power output of 150 megawatts, which maybe did I neglect to put that in here somewhere? Probably did. So let's see here. W.net equals 150 megawatts. There we go. And let's see here. Operates between 10 megapascals and 10 kilopascals. The efficiencies for the turbine, the efficiency for the turbine is 80%, and for the pumps is 95%. And didn't seem to write that? 80%, and the pumps are 90%. So 80%? No, not 95% is what the pumps were. All right, there we go. So we have basically the same process as always. We'll start off with, I guess I should probably label these. This is 1, this is 1, 2, 3, 4, 5, 6, 7. Yeah, that's right. Okay, so start off looking at 1. We know we have a saturated liquid. We know it's at 10 kilopascals. So we can get enthalpy and specific volume. We can get the work input to the pump then. And again, remembering to use the efficiency to get this value. Then we can get the enthalpy at 2 out of the pump. At 3, we have a pressure of 500 kilopascals. And we know that we also have a saturated liquid there. Okay, so coming in here, this is all at 500 kilopascals. So we can get the enthalpy and the specific volume. And then because we know the specific volume and we know these two pressures, we know then the efficiency of the pump, we can get the work, the specific work into the pump, and then we can get the enthalpy out of the pump using an energy balance on this pump here. Again, as always, we're assuming all this stuff is adiabatic except for the stuff where we actually want heat transfer. So we know P5 and T5, so we can get H5 and S5. We know S6 prime is S5, so the isentropic case. We know P6, and really that's whether there's a prime on there or not is irrelevant. Let's see if I can get in there. Well, all right. Okay, so there we go. So we know the pressure there, and we know the for the isentropic case, we know the entropy. So we can get the isentropic enthalpy at 6. So that would be this point here, 6 prime. And then we know the efficiency of the turbine, so then we can get the actual enthalpy at 6. This is that. And then we can basically do the same thing at 7. So we know the enthalpy in the isentropic case, the enthalpy at 7 prime is the same as that at 5. We know the pressure. So we're in the 2-phase region, so we can get the isentropic quality factor and the isentropic enthalpy there. And then again, using the efficiency of the pump, we can get the actual enthalpy at 7. Now we look at a energy balance on the what do you call it? The what is the name of that thing? The feed water heater, right? The open feed water heater. That's what we got here. An open feed water heater. Energy balance on this: energy flow in, energy flow out. And that allows us to find this mass flow ratio of m.6, which is this coming off here, to m.3, which is what's coming out of here, and which is also what's going into the turbine. So we find out that that ratio is 0.1718, which is basically saying that we're taking about 17% of the steam out of the turbine here at 6. Now, now we have enthalpies everywhere, so we can get the heat transfer in, which is just the heat transfer from the enthalpy difference in the boiler, and the heat transfer out, which is the enthalpy differences in the condenser. So but we don't have the full flow flowing through the condenser, so we need to get this on a kilogram basis of kilograms of flow going through the turbine. We need to multiply by this factor. This gives us basically the heat flow per kilogram of fluid flowing through the condenser, but we don't have that's not the same as the amount of fluid flowing through into the turbine. So again, that's what this factor is all about. And so we can get the net work in out, and that's this minus this. So we get the specific net work out is about 939 kilojoules per kilogram. Since we know the power output, we can get the mass flow rate, and that winds up being roughly 160 kilograms per second. The thermal efficiency is then just the net work out divided by the heat transfer in, or the specific net work out divided by the specific heat transfer in, and that winds up being 34.5%. Now, they also asked us for the irreversibility associated with the regeneration process. So we know P6 and we know H6. We didn't find S6 before, so we can now get S6. We can also get S3 and S2. Let's see here, by just looking those up, because we know the enthalpy and the pressure at 2, and at 3 we know that it's a saturated liquid, and we know the pressure. So again, we can get these enthalpies from the information we know. And then the irreversibility of the regeneration process is just S3 minus Y times S6 minus 1 minus Y times S2. Again, just getting all these things on a per kilogram flowing out of the feed water heater. So we had S3, we had the full amount coming out. At S6, we have Y times the amount coming in, because we took a percentage off here. And then at 2, we have the 1 minus Y flowing in. So that's where we get these terms. And calculating all that, we get 39.25 kilojoules per kilogram.